Okay, so last time we started talking about chapter 4. We introduced a sample space, events, and how to get a probability. And we talked about this idea of sets. And then we also talked about multiple events and the idea of and or. And so we're going to look at this, how we would actually collect data. So if we had a sample, we would probably organize our data in a table. So perhaps we asked males and females, if you were right or left-handed. And so we're going to try to work on events off tables in this format. First thing we like to do is always get the totals. So we're going to go ahead and add these guys vertically and horizontal. And it's always a good idea to add them both ways to make sure we get that grand total there. And so let's try one of these probabilities. Okay, so we're going to select one person here at random, and then we want to know what is the probability that the person is a female. And we're going to use this notation of P of F in this case. And so since we have our totals, we actually see that the females, the total is going to be 48 from our females column right there. And so we end up with 48 out of 100 because that's our grand total. And we're going to continue doing probabilities to about 4 decimals when possible. This one just goes to 2. And let's try another example here. So what if I want the probability a person is male and right-handed? So now I'm doing 2 events. And so our notation, probability a person is male and right-handed. And so male and right-handed, again, we're going to see that we're looking at the males and right-handed here. So there is that overlap. That's what that and is. So those 43 people. And it's going to be out of the grand total in this case still. And so we could kind of see that if we were to color them kind of blue and pink there, we would kind of get that purple region there. So that's that overlap between the and case. Let's do one more of these, the or case. So the probability a person is female or right-handed. And our notation for that will be probability female or right-handed in this case. And if you recall last time we had a formula for our or case, which was the probability you're female plus the probability you're right-handed minus the probability you're female and right-handed. So minus that overlap there. And this is helpful again if we don't have a diagram. So we're going to go and look at females and right-handed there. And so we see that if we're looking across at females, our total is going to be 48 that we have there. And it's a probability, so we want to still put it over 100. And then that we're right-handed, since we've already added up those totals, that's going to be 87. And again, a probability, so over 100 there. And we're going to subtract that overlap, if you could see from those pink marks, right-handed and female. We see that that overlap is going to end up being these 44 right there. And so we counted those 44 people when we counted the right-handed and also when we counted the female. So we have to subtract it once. And that's going to give us 91 out of 100, which is about 0.91. Now, don't get too caught up on the formulas. We could actually just see these by drawing the lines that we're doing right-handed females, and we could kind of see that overlap happening there. Okay. So here is some more data here. We're going to do the same thing and select one person here at random. And we're going to want to find a couple of these probabilities here. So find a probability that they stretch. Let's also do another one here. Find the probability that they had no injury. We're also going to try to find out the probability that they stretch and had no injury. We'll do a couple more here. And let's also find the probability they stretch or had no injury. And that's going to be the key thing here that we're saying or had no injury. And then we'll go ahead and find the probability they do not stretch or had an injury. And so the key things to look out for here are going to be the ands and the or. So and, or. And let's go ahead and number these. And we'll look for those guys there. So if you want to pause the video and give these a go, and then I'll come in and work these out. Okay, so probability that they stretch is going to be the 350. So we could actually just see that from the total. Probability that they had no injury, once again, no injury is going to be the 514. So we can actually see that from these numbers here. So stretching was the 350. And then no injury was a total of 514. And it's always out of that grand total there of the 800. Let's get to a little bit more tricky here. Now we're going to go ahead and do the AND case. And so for the AND case, we're going to be looking at the probability that they stretch and had no injury. And again, we're looking for that overlap, which is going to be that 295. So we're looking right at this overlap there, because it's an AND. For this next one is an OR. So we're trying to find a probability that they stretch or had no injury. And in this case, if you recall, it's going to end up being, we could use our formula again, but we'll try to do it a little bit more intuitively here without having to write the formula out. So what we want to look at is the probability that they stretched is going to be those 350 there. Then we're going to go ahead and say no injuries, which is a 514. But if we notice, we're double counting this group here, these 295, so we're going to want to subtract it. And so that's what we showed there. And so we'll end up with the 569 out of 800, which is roughly about 0.7113. And then let's try one more here. Let's go ahead and find this probability of the OR case. So here in blue, that they had did not stretch or had an injury here. Let me just write this out here. And again, a bit more intuitive without actually having to write out the formula. But we're saying those that did not stretch is going to be the 450 right here, because that's our did not stretch. That's our NS group, so no stretch there. And then we're going to go ahead and say then those that had injury. So injury, we're looking at a total of 286 there. But if we notice, this group here is going to be double counted, those 231, so we're going to have to subtract those. And so that's going to give us are 505 out of 800, which is roughly about 0.6313. Okay. Now let's look at mutually exclusive. So a couple of definitions here. And so mutually exclusive events are events that cannot occur at the same time. And we sometimes call them disjoint. And here's kind of an image for them in our sample space. So two events, no overlap in there because you're either in one group or the other. And an example is you're either a freshman or a sophomore. You can't be in both groups. If it's not disjoint or not mutually exclusive, then we'll have a picture like the Venn diagram that we're used to drawing where there is an overlap. And if you recall, this is with the formula. So probability of A plus probability of B minus that intersection portion there. And it turns out we actually have that same formula for a for two disjoint events. But since there is no overlap, we're actually going to go ahead and say that that piece is equal to 0. So we're talking about two events here, and we're saying they could either occur at the same time or they could not occur at the same time. So mutually exclusive and then not mutually exclusive. And so let's go ahead and make up an example for this here. And so let's say we did a survey and we collected some results here. We looked at males, females, and saw what type of beverage they preferred or what type of cola they preferred. And here are the totals. So, or the tallies, so 15-18 for Pepsi, 12-9 for Coke, and 2-1 for RC, if anyone still drinks that. And what we want to do always is let's go ahead and do the totals. So that's always a good habit to get done here. And we're going to select one person. And when we get these totals, it's always a good idea to go ahead and add them vertically and then also add them horizontally and double check that we're getting that 57. If you get the 57 twice, then you know you didn't do a goof up or so. So that's always a good check. And so let's find the probability the person likes Pepsi or is a male here. So the notation, probability a person likes Pepsi or is a male. And again, we're looking at the OR case here. So our lines, notice they're going vertical and horizontal in this case. So we're going to go ahead and use our formula here. And I'm just going to write it out. But again, we want to start kind of doing it a bit more intuitively and just looking at our table here. So for the OR case, we're going to go ahead and find out how many like Pepsi, which is going to be 33 out of our total. And then how many are males. And so that's going to be out of our total as well. And then we're going to subtract any overlap, which we could see is going to be those 15. And so we're going to go ahead and subtract those. And we're going to get about 8246 or so. Okay. Now, these events here are not mutually exclusive because you could be in both groups. You could like Pepsi and be a male. So let's look at another example here. So let's find a probability that a person likes Pepsi or Coke. And so we're still doing the OR case here. And so we're going to go ahead and do the same idea. We're going to do those who like Pepsi plus those who like Coke and then minus any overlap here. So those who actually like Pepsi, it's going to be 33 out of the 57. And then those who like Coke is going to be 21 again out of the 57. Now notice that these guys are mutually exclusive. So you're either in one group or the other. And so that overlap isn't going to exist. It's actually going to be 0. So we really have no need for it in this case. And we could work out that probability this way. So for disjoint or mutually exclusive, notice they're both groups, they ended up going vertically. So there's no way they're going to overlap, as opposed to one horizontal and one vertical. You're going to get that overlap there. So that's kind of a nice way if you're just drawing those lines in your table to try to get those.